Hey, Shannon.
Hey, Shannon.
Hey, Shannon.
What did you say?
That was nothing else.
Okay, you are old enough to know that you don't need to ask me about your binders, so do whatever you want with your stuff, because the test at the end of the year is due. This is the beginning of chapter 4. Although the first homework assignment is not in chapter 4, it's just kind of something that I have just found that if I do this before we start chapter 4 is better. Okay, and none of it's, I don't think, particularly hard, but you just got to make sure you have a good handle on it. Okay, here's a key concept. When a function increases, we're talking about increasing, which you refresh. Okay, when a function increases, its derivative is positive. Those two things go hand in hand. And when a function increases, its derivative is positive. So, for example, if I say f of x increases, then you can say, well, that means that f prime of x must be positive. Those two things are the same thing. Does that make sense? F prime is slope. Yes, increases, positive slope. Okay? So it doesn't matter what you name it. If you say that g of x or g of k, change it up. If I say that g of k increases, then we would say that g prime of k is positive. So what if I say that a function whose name is f prime increases? The function's name is f prime. F double prime. The derivative of f prime must be positive. You'll note the arrow I've drawn goes both ways. So if I say the words f the function increases, or if I say f of x increases, then I would expect you to be able to reply that that means that f prime is greater than 0. Likewise, if I say f prime is greater than 0, I would expect you to say that means that function increases. Does that make sense? Okay. So we could write the same series of statements for decreasing. When a function decreases, its derivative is not positive, but is negative. These are two different statements. One one says the function f decreases, and the next one says the derivative of f decreases. They're two different statements, but they have a corresponding statement that means the same thing. Okay? Good. So what the heck does this mean? Graph, if I have that written down, what are some possibilities that the graph might look like? Well, graphically, if I say f prime is positive, that means that there is a positive slope. Yes? So what would be some examples of a positive slope? Nice and simple positive slope? Very good. I'm going to draw the pictures instead of writing quotes, okay? That would be correct. Okay, nice straight line, all on the street. Okay? Can you draw a curve that has a positive slope? Only a positive slope. Can you draw a curve on your paper that has a positive slope? At every point on it, the slope is positive. Like that. Every point on that curve have a positive slope? There's one more, and that would be this. So can you see that this one do not look alike, but they both increase? Okay, you should have learned some language last year to describe the difference in how these two look. Does anybody remember? concave up and concave down. We're gonna come back to that in a few minutes. Okay. So, likewise, if I say f prime of x is less than 0, that means that it has a negative slope. And again, I'd like to get 3 little samples of that here. Make sure that if you're supposed to draw a picture for me and it's supposed to have a negative slope, that it's either straight, decreasing, or it's concave up and decreasing, or it is concave down and decreasing. Okay, little segments. What does it mean to say this? Okay, but the derivative is increasing. This tells us that f prime is increasing. Okay, so I want to draw a picture for you of a section of a graph where f prime is increasing. Now, I'm first going to draw you one where it's not increasing. Like right here, this is a line, a straight line. If I tell you that the slope right here is 2, then what's the slope right here? And what's the slope right here? Okay, this is f prime constant. F prime is not changing. Okay, F prime is not changing. I'm going to draw you one where the slope gets a little bit bigger as you move to the right. Okay, as you move onward to the right, the slope increases. So if I ask you to draw that for me, I bet most of y'all can figure that out pretty quickly. So I'm going to just put some fake numbers on here. Let's just say that that slope is 1/2. And I moved over here and said, well, what can you tell me about that slope? The answer is, it's bigger than 1/2. Yes? It's more steep right there. Does everybody see? And what we're really looking at when we say that is the slope of the tangent line. Okay? So that slope might be 1. And maybe when I get up here, the slope might be 2. As you move progressively to the right, the slope increases. Okay? There's another one where that's true, and it's less obvious, right? And it looks like this. And everybody's first instinct to say, that's not increasing, that's decreasing. And the answer is, well, that graph is decreasing, but let's consider what the slope is doing. Let's just say that this slope is -2. Kind of steep right there. I'll agree it's negative, yes? And if I move over here and take a look at this slope, this tangent line right here, it's still negative, yes? Is it going to be more like -3, more like -1? -1, okay? More like -1. And if I move even further over here, still negative. Move that up straight over. Okay? It's still negative, more like -2 or more like -1/2? -1/2. If you look at these three values, as you go from -2 to -1, -1 to 1/2, those numbers are increasing. And that's not immediately obvious when you first start. Your brain says, oh, it's decreasing. Graph is decreasing, slope is increasing. Okay? When you look at these two sections right, well, one more thing that's right. I'll say that. So let's take a look then at what this would mean. F double prime of x is negative. F double prime of x is negative would mean that f prime of x must be decreasing. And again, we could draw this line. That line is decreasing, but if I tell you that that slope is -1, then everywhere on that line, the slope is -1. F prime on this line is not decreasing. F prime on this line is constant. Okay? And you draw me a section of the graph where as you move to the right, the slope gets smaller than it was. So you want to start steep, and you want to get less steep as you move up. It looks like this. So, for example, the slope might be 2, it might be this. It might be 1, it might be, there's 1/2. Okay, slope is decreasing. And there's another way you can draw it that's less obvious. Okay, that's obvious, the slope is decreasing. And that's this way, where this slope is -2. Okay, -1, and then here it gets steeper, -2, and here it gets steeper, -3. And again, as you move from -1 to -2 to -2 to -3, it is, the slope is, I'm not supposed to say it, the slope is decreasing. Okay? So taking a look at the two different situations, you find this constant one, that's just there to remind you that this situation right here, the slope is not increasing or decreasing, it's constant. Taking a look at the two things, can you think of one vocabulary phrase that describes the shape of those two? Both of those pieces, instead of being concave. Which way? Up. Okay. Up. It's up. Concave up. Yes? Concave up. And if you look at these two right here, that same kind of vocabulary to describe them would be concave down. One way to tell them apart, I always have a few people who are like, I don't know how to tell them apart. When you draw the tangent line, if the tangent line's on the above them, if you put a tangent line on these, you see how that tangent line is above, then it's concave down. Okay? If you draw the tangent line on it and the tangent lines are below, then it is concave up. So that's one way you can do that. Okay? All right, so let's consider this shape. Nice little, just like a parabola. Yes. And what I want to look at this and do is describe, notice I'm not putting it on a piece of graph paper, not going on an x and y axis. So I can't talk about its values. I can't say if x is 2, what's y. That's not possible because I'm not giving you enough information. But can you tell me, discuss with me, what is happening with f prime in this graph? What is it doing in terms of positive, negative, 0? So what happens first? What is f prime first? Positive, negative, or 0? Positive. And then right here, f prime is 0, right there at the top. Yes? And then on this side, we can say that f prime is negative. Okay? It increases, it's flat, and it decreases. Okay. What can you say for me about the second derivative? Okay, so this is kind of our new concept, not something you've really done a lot, did a little bit last year. Okay, the idea here is for you to learn to recognize that I'm asking you about the second derivative, I'm asking you about its concave. That's what the question is. So when you look at this picture, is it concave up or concave down? It's concave down all the time, right? So if it's concave down, if you can see that it's concave down, what you've got to learn is to take this and translate it into what does that mean about the second derivative. Concave down means that the second derivative is negative. That's what we've got to be able to do. Do I see? Yep. And we do the same thing for a couple of other shapes.
So the first derivative changes usually, or does it change what the second derivative does?
In that case, let's look at 3 or 4 before we make any big generalization. Okay? So here's a nice little graph with a sharp turn instead of a nice smooth transition. Okay? So looking at this graph, we'll talk about the slope point. Where does the slope start out? It's positive or negative. And then what happens to it? Yeah, it's undefined. Or you can say does not exist. Right there at that point. And then on the other side of it, f prime is, no, f prime is negative. Okay, f prime is negative. Okay. When I look at the concavity, you have to see that this is a place of possible change. It's a place where something wonky happens. In this case, it's a sharp turn. There's several wonky things we can see. Sharp turn, vertical asymptotes, holes, gaps, all those kind of wonky places we have to think of as a possible problem. So when we talk about the second derivative, we have to talk about the second derivative before that wonky point, and we have to talk about the second derivative after that wonky point. Does that make sense? Okay, so before it, is it concave up or concave down? How many of y'all feel like when you look at that, you can tell me really quickly what the value is, concave up or concave down? Okay, if you have a problem with it, draw a little tangent line. If the tangent line is below it, then it's concave up. Okay, moving away. All right, so it's concave up, so that means the second derivative is greater than 0. And then after the wonky point, is it concave up or concave down? Again, with that little tangent line there, above the tangent line, so it's still concave up. But these two pictures don't look alike, okay? The other one's just concave down the whole time. This one's concave up, has a little strange place, and then it's concave up again, okay? So another kind of little strange place is a vertical asymptote. So I'm going to slap a vertical asymptote in there. No x-axis, no y-axis, but there's a vertical asymptote in there. Another wonky point. Okay? So before the crazy place, f prime is positive. At the crazy place, f prime is undefined, and after it, f prime is negative. We do the same thing for the second derivative. The second derivative describes concavity. You have to incorporate these goofy places, sharp turns, and vertical asymptotes. If there were holes or gaps, we have to include them as well. All right, so what's true about f double prime? What's true about the concavity before the vertical asymptote? It is concave up, therefore f double prime is positive, greater than 0. And after the vertical asymptote, it is still greater than 0. Okay? I want to stop and just point out, if you look at the information that we've written here, it's the same. Yes? So this information is not enough to tell us which one of these things is happening. We need a little bit more information. But yet, you can see how they kind of have the same shape. Yes? Except for one of them meets and the other just kind of keeps going up further.
Wait, why is the third one?
This one? Right here. Oh, I wrote it wrong. Oh. Right there. Hey, in front of it. Did I fix that? Or did you all write it down correctly? Right. Okay. So let's take a look at one that doesn't have a crazy funny point. You don't remember what this means? Horizontal asymptote. Not quite the same thing as vertical asymptote. Okay, horizontal asymptote. So, if you go to describe this, the question is, we want to talk about f prime. How many places does f prime change? Some. How many different places do we need to talk about? What is f prime all right in here, all of this? Positive. So you get right here, and it is, no, it's 0. Remember right there? Right at the very tip top of that, top or bottom, it's the slope is 0. And then over here on this side, f prime is 0. So we have to recognize that f prime is positive. There's a place where f prime is 0. And then there's a place, a section where f prime is negative. Y'all see that? Well, when we get to doing this, we're actually going to have it on graph paper, and we're going to have numbers to do it. But I need to see that you see the rise and the fall, and the slope is 0. Slope is 0 here versus the slope being undefined in the last two columns. Okay. The concavity is just a little bit trickier to look at. Okay, we'll get this thread off. All right. You're going to need more information to know exactly where it happens. But can you all see that at some point, the slope of the tangent line is underneath, and it switches then someplace to the slope of the tangent line within and above? Y'all see that? And I think last year y'all did some visual approximations of the the place where concavity change, does anybody remember the name of the place where concavity changes? Called a point of inflection, it's an inflection point. And so, right now, we just know it's somewhere in there. Would y'all agree? I don't know exactly where it is, somewhere. Okay. So, at the beginning of this, F double prime, concave up, so F double prime is positive. And then at some undesignated switch point, it inflects. And F double prime becomes negative. Okay? And if you keep thinking, well, where's that tangent line? It's above, it's above, it's above, and then all of a sudden it becomes below. So there's some other point of inflection over here. Okay? And it switches back to being concave up. We good? All right. The next few things are just some reminders. If I tell you that the limit as x approaches 2 from the left of the function is infinity, and I tell you that x approaches 2 from the right, the limit as x approaches 2 from the right of the function is also infinity, then what conclusion would you draw about the graph? Because you know that the limit from the left and the right of a specific value are infinity. What does that specifically say to you? What's happening in the graph? What kind of asymptote? There's a vertical asymptote too. So that means I'll put an x and y axis this time. But there is a vertical asymptote at 2. We absolutely know that. Okay? And we also know that as it approaches that asymptote from both sides, we don't know anything else, but we know that right here it's going up, and right here is coming from up. And we don't know what else is happening. So we don't, that's all it's telling us, is what's happening. Okay? And what if I tell you that from the left, derivative is infinity, I mean, the limit's infinity, and from the right, the limit's negative infinity? Then what am I telling you? It's an asymptote, okay? It's still an asymptote. Where's that asymptote? Still at 2. What's different is where the graph is going close to the asymptote. To the left side, it's going up, and to the right side, it's coming from below. And then there would be one where they're both from below, and we'll split the other. Yes? This is old. Look carefully at the difference in those two, because they are not the same thing. So a vertical asymptote deals with approaching an x value, a specific value. Okay? This is not approaching a specific value. When I say x approaches infinity, I'm telling you as the x increases forever and ever and ever. That means what's happening at the end. It's called end behavior. Y'all remember those words from last year? So this part right here is telling you end behavior. Not talking about a specific x value, it's talking about what's happening at the far right and what's happening at the far left. And I don't know if y'all did this exact notation or not last year, but I think it's pretty easy to comprehend what it's saying. This is saying as you get all the way out to the right, the y value, as the x gets really big, the y value gets closer and closer and closer to the number 2. That's what it's saying. The Y value is close to 2. So this is a description not of a vertical asymptote, but of a horizontal asymptote. The thing about vertical asymptote is the graph can't cross it. That you cannot go across a horizontal asymptote. That's not true of a vertical asymptote. Knowing that this approaches 2 at the end doesn't tell you a whole lot. I'm going to give you a couple of examples. It might look like this. There's one where the graph approaches 2 horizontal asymptote. Okay. There's quite a few possibilities. Eventually, you're going to need more information to figure out exactly what's going on. It could look like this, which is the same thing, just flipped over. Approaching 2. And it can even look like this. Something else. You saw one or two that look like this. You're kind of a pain in the neck to figure out. You can cross a horizontal asymptote. You just not allowed to cross verticals. Okay? There's no such thing as the middle, and then you go on forever and ever forever. So, yeah. That's just in our mind that we think there's going to be this symmetry into. That's how we're talking about in the middle. And I'm not going to say there's not usually, but it's not quite. Okay. There's a million kinds of graphs out there that are very long. Okay. And one last one. Right. So recognizing this right here, telling you that this is talking about in behavior. That is, it's giving you some information about horizontal asymptote. And recognizing now that it's not got the same horizontal asymptote at both ends. That as you get as x gets really big, y gets close to 2. But as x gets really, really small, y gets close to -2. And there's a couple of fairly common ways that can look. This is the most common. I think you probably saw this last year. There's that thing, that center thing, always a symmetric or really something symmetric, thinking about it. To the right, it never gets past 2, and to the left, it never gets past -2. But just to show you that there's not only one answer to anything. It could look like this. Okay. The next set of notes is on the handout. And you can do the handout from me when you get back before you watch this. And I'm going to ask you to do 2 different things with all of that information that I just gave you. First, I'm going to ask you to describe exactly where different things are happening using x values, okay? Using x values. So first of all, domain, and this is just a reminder, I have to keep telling my freshmen this all the time, but I'm not going to draw those arrows all the time. Okay, that's understood to go on forever and ever, even if you don't put them there. If I want this to say these stops, if I want this to have endpoints, I'll put little dots on the end. Okay, so the absence of a dot in suggests it goes on forever. So your domain is all real numbers. You can write that in any acceptable way. This is my favorite way, but you can write the words all real numbers. You can use that uppercase R that is all my children disagree about. Okay? Zeros at, the word at means at an x value. When I say at, you want an x value. Where does it happen? And this one's on not graph paper, but it's gridded so that you can tell what it is. So you've got 3 zeros, this one, and this one, and I'll give them to you. Negative 13, negative 5, and negative 1. There's the 3 x values. Okay, the zeros. The next question says, the function is positive on, when I say on, I'm looking for an interval. Again, x values, okay? Where is the function positive, where is negative? We did this in Alpha 2, freshman year, okay? So, I usually just run across the graph. I start at the beginning. This section of the graph is negative, so that goes here, negative infinity until I get to that first 0, negative 13. Everyone doing this? Okay, and then the next part is above, so that's negative 13 until you get to negative 5. And then it's below negative 5 until you get to negative 1. And then it's above negative 1 to the end of forever. And I'm pretty sure the triple made you put the union thing between them, right? Okay, so good thing to know. Maybe people don't care about it, and therefore it's fine. Okay, you put it in the don't put the other one, right? All right, so that's one thing. Where's the function positive? Where is it negative? The next feature is going to be relative maxes and relative mins. So the relative max here, the relative min here. Again, the word at tells me that I want x values. Count that, negative 9. Yeah, negative 9. Okay. And the relative min looks like it's at x equals negative 3. Now, they might ask you name the relative max, and you would have to give it x and y, but a lot of times it just says at, just for the x values. And these maxes and mins separate the graph into places where it increases and decreases. Okay? Again, we did this in algebra 2. Alright? So, again, I like to start at the beginning. What's it doing first? What's that? What's it doing? It's increasing. So that's negative infinity until it gets to negative 9. And in the middle of the graph, it decreases. Negative 9 until it gets to negative 3. And then at the end of the other end of the graph, negative 3 to forever, it increases. Okay? All right, the last thing is to talk about points of inflection and concavity. And to that end, I'm giving you, again, just sort of a visual estimate. We know the point of inflection is somewhere in there. I'll put that big circle. Yes? So it looks like I'm telling you to use this number right here. Does that make sense to everybody? Okay, just because we're getting an estimate from the graph. So the point of inflection appears to be at negative 6. And points of inflection tell us where concavity changes. So before the point of inflection, is it concave up or concave down? It's concave down, so negative infinity to negative 6. And after the point of inflection, it's concave up, negative 6 to infinity. Everybody good with this? Yes.
So, when you say at, how, like, will you tell us if you want a certain point? Or just say
when I say at, the relative max at, I'm saying give me the x value of the relative max.
so if you ever need a point, we'll look
Yes, it will say that. The calculus language is usually find the x value of the relative max, or it will say find the point that is the relative max. This is usually pretty easy to say. Okay? All right. So the next thing we're going to do is display this information in a different way. Okay? This way of displaying information is called an interval test. Y'all have seen it before. Okay? And notice that I have labeled my interval tests by what I am describing. The first interval test is going to talk about f of x. To go all the way back up to the top, the very first thing we talked about, the zeros, and we're going to put those on here. There's negative 13, negative 9, is that right? Thank you. And negative 1. And the idea is on this number line for you to tell me whether the graph is below or above by what you write on this number line, okay? And so looking at the graph, it starts out below, above, below, above. And this information here basically is the same thing as this information. It's just written in a sort of more concise form. Does everybody get the idea? And neither one is better, they are the same, right? The second one we're gonna look at is F prime. So now we're not looking at whether the graph is above and below, we're looking at whether it's increasing or decreasing. So we don't put the zeros on here, we put the maxes and the mins. That's where the -9 was, is that right? And -3. Okay, so now you're going to tell me increasing and decreasing. Okay, so what does the graph do at first? Increases, decreases, increases. And the way you know whether you're talking about above and below or increasing and decreasing is because you're going to label them. All right, so that everybody knows what you're talking about. Okay, F double prime is concavity. On concavity, you're not going to put the zeros, and you're not going to put the maxes and the mins, you're going to put the points of inflection, the place where concavity changes. And that number was at -6. Try to line them up. Doesn't have to be perfect, but try not to put -6 between -3 and -5. It will confuse you. And then you are going to describe to me whether it is concave up or concave down. Now, you can write up and down if you want to, but what you're going to get from me is going to be pluses and minuses. So at the beginning of this graph, it is concave down, and at the end of the other end of the graph, it's concave up. Does everybody see? Yes? I think on the homework, you have to do all of these things once or twice, and then I just pick some. Just the ones I ask you. That's a little bit more complicated. All right. So what does the second graph have that the first one didn't have? Vertical asymptotes. Okay? Vertical asymptotes are places where anything can change. And it has to be included in every single step along the way. So when we're talking about the domain, we have to include that you can't be plus or minus 3. Okay? And I still got a 0 here, but I only got 1. X equals 0. This question says, where is the graph above the x-axis? Where is the graph below the x-axis? It starts out below. At -3, it's not anywhere, so you have to skip over that. Y'all have to see this last year, right? And so it continues to be below until it gets to 0. At 0, it's not above or below, it's on. Move that out. And then it's above from 0 to 3, and then from 3 to infinity. That makes sense? So I'm going to skip this, I'm just going in a different order. We're down to the bottom, there's my number line. What numbers need to go on our number line? What were the critical pieces of information for above and below? -3 and 3 have to be on there. And also, 0. So the zeros and vertical asymptotes. And the place where people mess up the most often is with these vertical asymptotes often, and nothing makes any sense. This graph is below, below, above, above. Right? Relative max. Not 1. So, think that doesn't exist. Relative min, it doesn't have 1. Okay? Increasing and decreasing. And what's it doing first? That's just the best my poor old computer can do. It's decreasing. So it starts out decreasing until it gets to -3. And then on the other side of -3, it increases. -3 until where? You know, we're going to be a little bit picky right here. Right there, it's flat. Right there, it's flat. You have to learn how to recognize that versus one that looks like this. Which also changes concavity, has that little jig in it. Yes, that little point of inflection. So you can see how it's not flat right here. So we're going to be a little bit picky about that and say it's not actually increasing at 3 or decreasing at 3. Did I do this backwards? Yeah. You'll do that sometimes. Sorry. So it starts out decreasing. I'll have to pick up that 0 as a place where it is not increasing and not decreasing. And then on the other side of 3, it decreases. Okay? Good? Alright, so slide down here and do this one. Okay, what numbers need to go on here? -3. If we had maxes and mins, we would put them on there as well. All right, places where they can go up and then come down again, points or smooth ones. But you have to vertical asymptotes on there. So, this graph decreases. And then in the middle it increases, you know. I guess technically we should put that 0 right there. And then it decreases again at the end. Yeah, that really needs to go there. It's not an max or a min, but it's a place where it flattens out. Okay? Right, now what is, point of inflection? Places, a point, it's actually asking for a point of inflection. Is there a place, a point on the graph where it changes inflection, changes concavity? 0, 0. Okay, you might say at x equals 0 if it said where is it, okay? But there are two other places where the concavity can change, and that's at the vertical asymptotes, okay? And so they have to be included in our discussion. It's concave down, and then it's concave down again. And then it's concave up, and then it's concave up again. So you have to include the vertical asymptotes in your discussion of concavity. Right? And what needs to go on our second derivative test? It has to go on all of them. Vertical asymptotes. They have to go on all of them. And any other points of inflection. Okay, again, 0. Y'all see how important it is that you label when you have these underlines on your paper to make sure that it's clear what you're talking about. Okay. The other thing I'm going to ask you to do is I'm going to give you some information, and I'm going to say, starting to scratch, because it's the beginning of the year. Okay? So I'm going to give you some level of information. The two that I've done for practice are fairly slim. Some of the ones I gave you for homework are a little bit more detailed. So here I want to just make sure that you know everything that I'm telling you. Domain is all real numbers. What are these two? What are these right here? Those are the points. They're the 0.3, 0 and the 0.7, 0. You also are to assume that if I've given you zeros, that it says and no others. Does everybody understand? Okay, that I'm going to give you all pertinent information. All right? Okay. What's this right here say? F prime at 5 is 0. The slope at 5, okay? The slope is 0. So what does that mean? It means it's flat. Okay? And then down here, what is this saying? F double prime is negative. What is that telling you? Concave down. The whole graph is concave down. Okay? So you look at every bit of information. Okay, this says that the graph rises and then falls, and this says that the graph is concave down on the whole thing. So you get a sense of what the picture looks like. Okay? When you go to draw these, x and y axis, I think I might have drawn them for you. Put your points on the graph. Please, I'm going to take the points off. I'm the guy for anybody who does this. I really am. Not allowed. Anybody do it. You gotta stop, okay? I'm not saying it's never okay, but most of the time you don't need it. I know 3, 0, 7, 0, that's good enough for the space between them. It rises and it falls. Okay, where is it flat? 5, which is between 3 and 7. So put a dot up there somewhere and make it flat. Okay, it rises and it falls, and look at there, it's concave down. Did I see? They're not all that easy. Okay, none of them are that easy. Okay, let's see these. It's kind of like putting a puzzle together. So in this next one, what have I told you in the first place? That's 9.4. What are the possibilities? Possibilities, vertical asymptote. What is another possibility? A hole. Those are the two big ones, yes? I suppose it might be a gap. That's a possibility with 2 holes at the end of it. That's a possibility also. Well, what does this say? F of x does not equal 0. F of x never equals 0. What's another name for f of x? Y. Y never equals 0. So I'm telling you, no what? No x-intercepts, no zeros. That's what that says. So you have to translate, okay? What do these scribbles on the paper mean? There's no x-intercepts. Okay? What does that one say right there? Slope never equals 0. You should have no flat places on your graph anyway. No flat places on your graph. Okay? Alright, I haven't labeled these. This is acceptable. All my F prime stuff is lined up. All my F double prime stuff is lined up. If you like this format, but I will tell you that people will become confused when they don't remember which one of these is which. And you're more likely to remember it if you put the F prime and if you put the F double prime. I'm not going to mark off if it's well organized, but I'm just giving you. So tell me, what does the graph do? Here, what does it say? It decreases, and then something wonky happens, yes? We don't know what. And then on the other side, what happens? It decreases again. Right? What does this say? Concave down, and something wonky, and what does this say? Concave up. Okay? So you're learning what do these symbols or what do these structures tell us. There's only one important place on the graph, and that's the number 4. And we've decided that it's either a vertical asymptote or a hole. So you get to pick one and see if you can make everything fit. If you pick one, try to make everything fit, and it doesn't fit, then pick the other one and see if you can make it fit. Does that make sense? So which one you want to try? It's just a vertical asymptote. Okay? I need you to draw a graph that is decreasing and concave down on the left side of this vertical asymptote. Can you do it? Decreasing and concave down. This is where having those little bits and pieces clear in your mind are. There's this, there's this, there's this, there's this. This is concave. These are both concave down. Okay? Which one of them is decreasing? The first one or the second one? And pick that up right there. And pick that up right there. And move it over here. Yes? Get it? Okay, so I'm going to remind you of one other thing. Told you there weren't the x-intercepts. Look at the picture you drew. Did you draw an x-intercept in your picture? Can you adjust it so that it doesn't have an x-intercept? And I think you can.
Yeah, you can.
So, like, I bet anything that a bunch of you did this, right? Let me pick that up. Well, almost everybody does every year. Okay? Look here. So now, if you just take that and bring it down here like this. See? Okay, and then what are you automatically telling me is going on here, even though I didn't say it? What's it got? That's right. Say it louder. Horizontal asymptote. I didn't tell you that. Wouldn't it have been nice if I had told you that? Okay? But it became clear in making everything else work. Okay, on the other side, it does still decrease, but it has to be concave up, and it still can't cross the x-axis. So decrease and concave up. Here's your two. Decrease, here's your two concave up pieces. Which one is decreasing? First one is where you need to put it so that it never crosses the x-axis. This is my favorite one. I love it when people do this for me. I'm like, seriously? What's happening right here exactly? Yeah, did she do that? Seriously. Yeah, so that's not right. It needs to be up here. Yes, like that. Okay? That makes sense? Turn over on the back. How's this class over?
145.
Okay, so, last thing, my favorite. Something doesn't make sense. You have to learn to recognize when you have found bad pieces. Does anybody do jigsaw puzzles in here? Have you ever done a jigsaw puzzle where there's a piece missing? It's very frustrating. Have you ever done a jigsaw puzzle where at the end you go, this doesn't go in this puzzle. Why is this piece in here? That means you have small children, right? That's what that means. So, sometimes there's a mistake. Somebody's messed up. It could be you, okay? But you need to recognize it doesn't make sense. So let's start with what this tells us. F of 0 equals 3. 0, comma, 3. Look at there. I did that without 1, 2, 3. Okay? Let's do it. F of 2 over here equals 1. Don't go as high as 3. Put a 1 right there. Okay? Everybody see? Alright, now tell me what this is telling me has to happen. What does the graph have to do? Increase, increase, and increase. And tell me how come you know that something's wrong. There's no way to go between here and here without decreasing. Something's wrong. But you can't make it work. I don't care which way you convolute all those little shapes. It isn't going to work. So that's when you stop and you go back and say, oh, I lost my negative, and you fix it. Do y'all understand? Something's wrong. You're not going to fix it by like turning it upside down or twisting your hand backwards. It's not going to work. Okay? All right. Look at number 6. Give me 3 points. F of 0 equals 3. F of 1 equals 4. F of 2 equals 5. Okay. Now let's put one more somewhere. You know, I could just connect these with a straight line. All lines are straight. That would make sense for this piece of information here. Increase, increase, increase. I can do that. Yes? But what does this tell me? What have I written right here in my notes to myself? What has to happen at those 2 places? It has to be flat. Okay? So, graphs can be flat like this, or like that. Y'all see those flat places? And when you get ready to draw one, knowing that it has to be flat should be a slight exaggeration so that you don't accidentally not make it flat. Okay? Slight exaggeration. So, can I increase and increase and increase and those being flat? The answer is yes, I can. Not a problem. Okay? Then the next thing it says is you must keep everything concave up. Okay? When you come off of a flat place, like this, you can do one of 2 things. You can either go like this, or you can go like that. Those are the only 2 things. You may not come off of a flat place and go like this. Y'all see that that's not okay? Yes? Unless we know there's a shortcut. Okay? So, can I come off of this flat place and be concave up? Yes. Up, go. Alright? And then past 1, can I continue to be concave up? Yes. If I keep being concave up, am I ever going to run into this other flat place correctly? No. Okay. Coming off of this flat place right here, I have to come off of it at a concave down. Something's wrong. Y'all see? Either it's not supposed to be flat, or it's not supposed to be concave up. Alright? And this is where you go back and you say, what's not right? Doesn't all fit. Does that make sense to everybody? Okay. There's a homework packet. Goodbye, Shannon.